This is a tutorial on using Microsoft Excel Solver and Graph Grabber to figure spice parameters for N-channel MOSFETs. First thing I'm going to do is open up Graph Grabber. This is a free program and it's really quite simple to use. I've already taken a JPEG of the data sheet for the IRFP244 and I'll download it. I'm using the IRFP244 because Bob Cordell has that device in his book on power amplifiers. Now let's just enlarge the picture a little bit. First thing we have to do is set the x-axis. Okay, the program asks us for the minimum, 0.1. Maximum is 50, and it's logarithmic. Okay, we're going to set the y-axis. Minimum is 0.1 again. The maximum is 50 amps. It's logarithmic. I'm going to do one data series so that you can just see how the data is entered. You'll note here on the left hand side the points are entered as we click on them. There's okay, this is the current from the drain current on the left axis, and this is the gate to source voltage, 5 volts. Let's see what that looks like. Okay, pretty good. Export the data as an Excel file, and I'll call that MOSFET 244. Alright, close it. Now I've already downloaded the data into an Excel spreadsheet. Let me show you what that looks like. I've already created a graph. This is the drain source voltage, the gate source voltage, the current that we've observed. Now we're going to be looking at this transistor when it's in saturation. So what I've done is taken the final value of current, and when the transistor is pumping out 90% of that final value, 90% or greater of the final value, I assign a value 1 to this test. If it's less, I assign a value of 0. Okay, the formula for drain current is 1/2 kappa, a constant, times the difference between the gate source voltage and the turn-on voltage squared. Okay, and that's further adjusted by a fudge factor. This is the channel length modulation factor, 1 plus lambda times VDS. It results in a predicted value of drain current. And then I have my graph here of the predicted values using these variables. The threshold voltage, VTO, kappa, which will start with an assumption of 3, and lambda, 0.003. EX is the squared term there. Now what I do with that data too, there are a couple different ways of looking at the errors, and one is the sum of the squared errors, and the second is log squashed error, and third is to calculate the R-squareds. So to open Solver, first of all, you've got to download it. It should be on your C drive. When you go to the file option, you can manage add-ins, and Solver will show up there. When you want to use Solver, you go into the Data tab. It's right here. So let's use Solver. Now we're going to iterate. We're going to look for to minimize the log squashed error. So we're going to minimize log squashed error. Under Options, I want to see how the iterations proceed. So we're going to search the iteration results. You also wanted to enable automatic scaling. I use the Newtonian approximation, and you can adjust the amount of time, the number of iterations, precision, tolerance, and convergence here. Okay. Alright, so we're going to solve. Just move this down a bit. We're starting out with a log squashed error of 1.364 times 10 to the second. Okay. Alright, you can see how the values are changing. Log squashed error is now 2.884 to the 01. Okay, we've got a solution. And the log squashed error is 2.818 to the 01. The sum squared error is 2.919 to the 01. And the sum of the r-squareds is 4.195. Now what you notice, though, is that when the VGS is 4.5 volts, we're getting a very low predicted value of drain current. And that's really not satisfactory. Sum of the squared errors is not going to give you much better, but we'll solve for that just to show you how it's done. We're looking for a minimum. I have this in this box here, J6. Okay, solve. Okay, it's got an answer. It's really not that much better. Let's go into Solver again. This time we're going to set the target cell for the sum of the r-squareds. And this we want to maximize. Okay. Okay, you can see them starting to converge to reality pretty quickly. Now one thing you have to note is that you may get a really good r-squared, but it may not be the value you're looking for. So you have to step through it a couple times. You notice how these values, when the VGS is 9 volts, how it's diverging from that. Even though you're getting a good r-squared, you may not be getting something that will work in simulation. So we'll just continue until it finds a solution it likes. Okay. So now at the VGS of 4.5 volts, which is the lowest one in the data sheet, you see you have a very good r-squared while it's in saturation. Very good in the middle. Very good. This is VGS of 8 volts. 9, not so good. 5 volts, not so good. But it's close enough. When you perform this analysis with the sum of the r-squareds, you can take the values of the threshold voltage, kappa, and lambda, and insert it into the level 1 SPICE model, and you're good to go.